Hi, my name is Chloe Schneider, and I was funded by the North Carolina Space Grant to participate in a NASA-developed project focused out of North Carolina National Centers for Environmental Information, NCEI. My team members were Dean Berkowitz, Egla Ochoa-Madrid, and Julie Sorfleet, with our fellow was Andrew Shannon. And we were tasked with developing a composite moisture index utilizing NASA Earth observations for drought monitoring in the Missouri River Basin. The Missouri River Basin is one of the largest reservoir systems in the US and provides irrigation water to some of the most agriculturally productive lands in the US. And recently, drought events have impacted the resource availability and economic productivity of this area. Specifically, in 2017, a drought caused the loss of about $2.6 billion in the area. And a single drought indicator would be effective for resource management and decision making. So we partnered with NOAA National Weather Service's Missouri River Basin Forecast Center, Montana Climate Office, and the NOAA Regional Climate Services Central Region in order to achieve this goal. So we were intaking different spatial observations, and the NASA satellite observations we used were the Terra Modis NDSI snow cover and the SMAP soil moisture standardized anomalies. We also use Snow Data Assimilation System SNODAS products from the National Snow and Ice Data Center, and we use snow water equivalent and snow depth. So we had all these input variables, and we created monthly means for each data set, and then we computed percentiles based on the climatic histories of these data sets, and then categorized these percentiles into bins to relate to below normal and above normal moisture conditions. And then we sum these bin parameters for each month to input for our CMI. Notice that SMAP does not go through the same process because it was already in normals as anomalies. So we took our CMI was a mean of each of these data sets. Our CMI allowed for weighting each of these data sets a little differently, but we did not get to that step during this term, so each data set was weighed similarly. Our results, here is a pixel-based CMI of about 26 kilometer resolution. Darker red is drier than normal conditions, and darker blue is wetter than normal conditions. And March 2016 was a known drought year in the area. And then 2019 was a known flood year in many regions of the area, and you can see our CMI reflects this. Here's a HUC-based CMI. HUC is a hydrologic unit code, and it's just sub-watershed basins in the area. And we represented our data this way as well. To assess the validity of our CMI, we correlated CMI against spring discharge from USGS stream gauge locations. Here in this figure, you can see a subwatershed, which is the Yellowstone area, and we validated our CMI results for this area against spring discharge in yellow. Here are some of the results. R squared value of 0.4 for February CMI versus spring discharge, and then a CMI a R squared value of 0.55 for March CMI versus spring discharge. And so for the Yellowstone watershed, the February and March CMIs performed better than January and December, with an R value of 0.7 for March and 0.11 for December. And that's what you see here on the right is month versus Pearson correlation coefficient, or R. And after December, our correlation improved by month. So March was found to be more successful in relating to spring discharge. The CMI we deemed overall successful in reflecting general wet and dry conditions across the basin at both the pixel and HUC-based resolution. However, more analysis needs to be conducted to see the differences in each individual HUC region and how each individual HUC region CMI relate to spring discharge. So uncertainties and limitations of our project was differing spatial resolutions, limited historical records used to create climatic normals, assumptions about data distribution when putting our data into percentiles and bins, and then assumptions about physical geography when assessing our CMI at different regions. Future work for our project would be automated mapping of the CMI to be used in the future, expanded correlation analysis to understand differences in CMI versus spring discharge across each HUC, and then optimize the weighting scheme of the CMI, and as well as expanding seasonal variability of our CMI, because right now most of our input variables were snow cover and it is mostly used in the winter. SMART project was made possible through our partners and Ronnie Lieber, who is our science advisor from NCEI, as well as the North Carolina Space Grant, who funded me for this project. Thank you so much for listening.